Welcome back to the next session of power electronics. We were discussing about the introduction and thyristors. So, in detail we were in the last sessions we discussed about the turn on methods, out of which gate triggering was the best preferred method, and in gate triggering also by using various elements we discussed about the different firing circuits by which we can generate the gate pulse. So, out of that we have discussed resistance triggering and resistance capacitance triggering circuit. So, next type of triggering circuit is by making use of a device that is known as a UJT. So, this UJT is known as the uni junction transistor. Uni means it is one single junction transistor. So, we have come across BJT, a type of transistor, that is a bipolar junction transistor, which will be having 3 layers NPN or PNP and 3 terminals. Okay. Similarly, there will be 2 junctions in case of the BJTs, whereas in case of a UJT, uni junction transistor, here we are going to have 3 terminals, but we are going to have only one single junction. Okay. So, basically the basic structure of a UJT is it is having a lightly doped N region. So, this region what you can see here is a very lightly doped N region. Okay. Whereas to this lightly doped N region, when we are going to add a heavily doped P region. Okay. So, this forms one PN junction. This is nothing but one PN junction, which is consisting of a heavily doped P region and a lightly doped N region. So, we can come across only one single junction. So, that is known as a uni junction. Okay. Now, this point is also known as the X point. Here, whenever we are going to say that when this emitter is open, then what happens? Then this N region, which is a lightly doped part, will behave as a resistor. Okay. So, this resistor, interbase resistor, can be dragged into 2 terminals, that is base 1 and base 2 terminal. This interbase resistances, that is a combination of this, that is RBB. Interbase resistance is nothing but addition of these 2 resistors that are found inside the lightly doped N region. As this is lightly doped N region, usually the B1 and B2 resistor will be having up to the range of 4 kilo ohm to 10 kilo ohm resistor, high resistor. Okay. So, this 2 bases can be attached with the ohmic contact and 2 different terminals are given. So, in general, a UJT, uni junction transistor, consists of one single junction P and N and 3 terminal, base 1, base 2, as well as a emitter terminal is available. So, this constitutes the basic structure of a UJT. Next, coming to the symbol, when you can see the symbol here, this emitter slightly is bent towards the base 1 region. So, when this emitter is slightly bent towards the base 1 region, I will explain it to you later what happens here across the E and B1 junction. So, this is a basic symbolic representation of a uni junction transistor. Now, this is similar to that of a diode, the working is similar to that of the diode, but the speciality, the most significant use of a UJT is you can vary the output voltage. Okay. So, since this special feature is present in a UJT, UJT is usually used as a switch. Okay. So, variable voltage is possible, and for switching off either the oscillator circuits or the triggering circuits, or to generate the triggering pulses of SCR or triad, we make use of a UJT. And the switching time of UJT is somewhere around nanoseconds, the speed is more. When we consider the R triggering circuit, we saw that the R triggering type of circuit, we could use the firing angle. We could generate the firing pulses only from 0 to 90 degree. Whereas the RC triggering, what we saw by making use of half as well as full wave RC triggering circuit, we came to know that the pulses whatever we could generate was only within the range of 0 to 180 degree. But here the speed of the UJT, the switching speed of the UJT, the device which we are going to use in our triggering circuit itself is in nanoseconds. So the switching speed is more. Okay. So apart from R triggering and RC triggering, if we want the action, the switching action to be faster, or the circuit whatever we are going to build in for triggering an SCR, if it is a high speed application, then we prefer the UJT. Right. So this UJT is used only as a switch. Okay. Now the equivalent circuit of a UJT. So here we know that only one single PN junction is available. So this single PN junction is nothing but represents a diode. So this is the diode. So this point, and we have two resistors. So RB1 and RB2 are the inter-base resistors. So this can be equivalent to like this. Now, a generally bias, whenever we speak about any device, we study when it is going to be in the on state, when it is going to go to its off state, what is its symbol, what is its equivalent circuit, how we can bias the circuit. Let us say a normal biased UJT circuit. So here we have connected the UJT. So when you come across this circuit, you can observe that the terminals emitter as well as the RB2 terminal is always biased to a positive potential. Emitter and RB2 is biased to a positive potential, whereas this B1 is always taken, RB1 is always taken as the reference terminal. Okay. So this what happens whenever you are measuring any voltage across the UJT, in order to know what is the actual output, what is the actual output voltage you are getting across the circuit, you take this RB1 as the reference point. So to measure the output voltage, right. Now what happens when this biasing takes place? Okay. Now coming back here to this circuit, when this emitter is open here, okay, emitter is open means when the emitter is in the reverse biased condition. Okay, what happens when the emitter is reverse biased condition? Here this is open. Okay, so this RB1 inter-base resistors act as the voltage divider circuit. So now when you see you have not applied the emitter here, so you are going to provide the voltage, supply voltage, and coming to VBB and VEE, VBB voltage what you are applying is a fixed voltage. Okay, it is always a fixed voltage, whereas this VEE voltage what you are going to apply is a variable input voltage. Usually this VEE is nothing but the output of a capacitor. Capacitor voltage is considered. Okay. So in this generalized biasing circuit, we can see that when we have not connected the emitter, when the emitter is, or this diode, emitter diode is still in the reverse biased condition, then what happens? This point RB1 and RB2 are available, which is connected to a VBB supply. So this acts as a voltage divider rule. So at the point X, the voltage Vx is equal to RB1 divided by the resistors RB1 plus RB2 into the applied voltage VBB. So when the emitter diode is in the reverse bias condition, it acts as a voltage divider circuit, and we are going to get the voltage Vx is equal to RB1 divided by RB1 plus RB2. we know also that RB1 and RB2 is nothing but the resistance that is present in the lightly doped N region. So, this can also be represented as RB1 divided by RBB into VBB. Okay. Now, a new term known as the intrinsic standoff ratio can be used. Intrinsic standoff ratio is defined where eta is equal to the base resistance 1 to the total interbase resistors. So, eta into VBB. Instead of writing RB1 by RBB, we are going to replace by the intrinsic standoff ratio, that is eta, which has a range of 0.5 to 0.8. Okay. So, using this concept, what will happen to the equation of Vx now? Now, by replacing the intrinsic standoff ratio, we are going to get the finalized equation as Vx is equal to eta VBB during the off state. Means the diode is still in the reverse bias condition. When the diode is open, what happens? Across these two base, that is a lightly doped N region, we are going to, by connecting the biasing circuit with respect to VBB, we are going to get the equation for point Vx as eta into VBB, where eta is nothing but the intrinsic standoff ratio having a range of 0.5 to 0.8. Okay. Now, when this diode is forward biased means you can see so long, that is when this diode is still in its reverse bias condition, what happens to these interbase resistances? It is being applied with a positive potential of VBB, and hence it is giving some small output voltage Vx, that is eta VBB. Okay. Now what happens? This eta VBB is the voltage that is present only in the lightly doped N region. Now, when we say E or the diode voltage is forward biased, means we are going to apply a positive potential. You can see here VEE is applied to the emitter. Emitter is nothing but the anode of the diode. So, when you are applying positive potential to the positive P region, then what happens? Then this diode is having a positive potential, that is holes are in excess, you are applying a positive potential, repulsion of charges takes place. When the repulsion of charges takes place, whatever the holes present in this part, what happens? Already you have lightly doped, means only few free electrons are available in the N region. So, this P region has an excess of holes, heavily doped P region. So, there will the barrier that is created, the junction across the emitter and the base 1 region, it tends to move towards base 1. Okay. So, this holes start breaking the junction, and hence we say that the diode, this diode is in the forward biased condition. Okay. So, forward biased condition means at this point, that is during the forward bias condition, that is the reverse bias condition. Now, we are going to write the equation for forward bias condition. What happens? There is going to be a peak point, highest value of voltage. So, highest value of voltage is nothing but at the point X, we already have the voltage during the reverse bias condition plus the small diode voltage. Diode voltage during the on state, it can be around 0.6 or 0.7 volts. So, this equation just at the instant when the junction is broken, then we are going to get the equation, the peak value as Vp is equal to Vx plus Vd. Vx is nothing but eta VBB plus the diode voltage Vd, on state voltage drop. When the diode goes to the on state, what happens? There is a small on state voltage we are going to consider. So, this is the voltage that we are going to get during the forward biased condition of the diode. Okay. Forward bias condition means now we are going to provide the voltage to the emitter terminal. Now, when you are providing the emitter terminal, what happens? Positive potential and emitter, that is in the emitter we have a highly doped P region. Then what happens? There are excess of holes that are being created at this junction. It is a heavily doped region. And coming to the resistances, initially in the reverse bias condition, okay, Vx, we are going to get a small voltage that is available at the point Vx, but what happens to the resistance? The resistance is still high. So, here in case of the reverse bias condition, the value of Rb1 is still around 4 kilo ohm, still a high resistance. If there is a high resistance, what happens? The current flowing is very small. Okay. So, this is during the reverse bias condition. Now, coming back to the forward bias condition, when do we say it is a forward bias condition? See here, when you are applying the holes here, you are increasing the potential of VEE, you are injecting holes here. What happens? So, in the P region, the repulsion takes place. Due to this repulsive action, what happens? Whatever the free electrons were available, these holes make a pair with that. But we also know that N region is a very lightly doped region. So, only few electrons are possible. So, hence the current will be flowing here. The resistance also, the resistance Rb1 decreases. When the resistance decreases, then what happens? The current increases. Till where the current can increase? Till it reaches some peak value, because the current is possible only when there are more electrons. Here we have less electrons. So, until all the electrons are paired with the holes, there is a flow of current. Now, what happens? You are still giving some voltage here across VEE. When you are still applying the voltage across VEE, what happens here? There are holes that are being created here, and which just gets accumulated at this region B1. So, now what happened? Whatever the holes you are applying here from this VEE region, this is getting accumulated around this region. So, what happens? The resistance, it decreases. Okay. So, the resistance of this Rb1 is going to get more, it is going to go down, okay, because of this accumulation of charges here. Okay. Since this resistance, because of the accumulation of charges in the Rb1 region, what happens is a negative resistance comes into picture. To understand more about this negative resistance, we have to study the VI characteristics of UJT. I hope till now you have understood how the emitter diode is forward biased and how it is reverse biased. Starting from the reverse bias condition, what is the equation we got, and when it is forward bias condition, what is happening to the emitter diode. This is what we have studied so far. Now, for the VI characteristics, let us draw the VI characteristics based on this concept. Coming back to the VI characteristics, we have already studied the biasing part, how it is going to be turned on and how it is going to be turned off. Now, we are going to study how the VI characteristics of a basic UJT lies. Okay. So, now when we are studying the basic operation, coming back to the off state, reverse bias condition, when we are going to give the VBB voltage, initially there will be some voltage available at the N region. N region is a lightly doped region, so a very small current will be flowing here. Okay. So, let us call it to be the leakage current. As you increase the VBB up to some value specified, constant or fixed value, till then what happens? there will be the reverse current flowing. Okay, at a point till where? Till you are going to apply a potential, that is VEE is applied across the emitter. Till where? Till the point when this voltage applied from VE, this voltage is greater than the Vx. Okay, so this region till this part is when the voltage Vx is greater than VE. Vx is greater than V means the VBB voltage is higher than the applied voltage VE. Okay, so during this time the UJT is in the off state. Okay, and we are going to get some voltage Vx. Okay, now what happens at one instant of time when this voltage Vx, the applied voltage Vx is equal to, or VE is equal to Vp. When do we say that by the UJT is in the on state? When it comes across the voltage Vp. So, when it is going to come across Vp? When VE is equal to Vp. At this instant of time, what is the equation? When the voltage VE is equal to the peak voltage. Only at this instant of time UJT goes to its on state. Okay, so now what happens? We are going to get the peak value, maximum value. So the peak value, peak voltage corresponding to the peak current. Now what happens? Already you have broken the junction here, you have allowed the holes and electrons to make pair. There is a high current flowing here. See the current keeps on increasing, but what about the voltage VE? VE keeps on dripping down. Why the dripping of voltage takes place? Because you are providing this VE voltage across the UJT. So what happens? The holes gets accumulated here. So this part is known as the negative resistance region. The voltage dips. Okay, but the current is still in the increasing part itself. The current keeps on increasing till where? Till there is some saturation. So till all the available electrons or available holes have been accumulated here in this region, B1 region. So till there will be some minimum voltage. That minimum voltage is known as the valley voltage, and the corresponding current is known as the valley current. So this is the minimum voltage that can be applied across the UJT. Now further, what happens? Further you are increasing the voltage. At some point what happens? Slightly there will be an increase in voltage as well as the current up to the saturation point. So for every transistor we know that there will be a saturation point. So till the UJT attains its saturation point, till there will be a slight increase of voltage and current. This is what you are observing in this graph. Okay, so the corresponding current is the emitter saturation current. Corresponding voltage is the emitter saturation voltage. Okay, so there are three different regions of operation. When the value of Vx is greater than the applied voltage or the emitter voltage VE, the UJT is said to be in its off state. It is also known as the cutoff region, where there will be a reverse leakage current flowing from the VBB towards this lightly doped N region. Now at the instant when the UJT is going to go to its on state, then what happens? At that instant of time, Vp, the voltage should be equal to V peak. So if the emitter voltage is equal to the peak voltage is nothing but Vx plus Vd, where Vx is nothing but eta VBB plus Vd. Only at this instant of time you are going to say that UJT is in its on state. Okay, and we can also observe here Vp is equal to, Vx is nothing but eta VBB plus Vd. Okay, VD, diode voltage, when it goes to the onset, it is a fixed value, 0.6 or 0.7, it is fixed. Intrinsic standoff ratio is also a ratio which is fixed, 0.5 to 0.8 is the range of it, okay. And then whenever you vary VBB, what happens? VP varies. So the link is between these two, VP, VBB. You vary VBB, VP also varies, okay. So here at this point when it is equal, UJT turns on, and as you keep on varying the voltage, slightly the VE keeps on decreasing, but the current is still in the increasing range. So this part, when the resistance decreases, that is known as the negative resistance region. It is this part of the UJT that we are going to make use as a switch. Okay, later I will tell you in detail about how we are making use of this negative resistance region in our switching action to generate the pulses across to supply to a thyristor. Okay. Next, from the valley point till it reaches its saturation value, this region is known as the saturation region. So this is the general characteristics of a UJT. This you have to know in order to study for UJT as a triggering circuit. These are the prerequisites which we have discussed. Okay. Now in detail we will see how we can make use of this device UJT to generate our triggering pulses. So the topic which we are studying is generation, the different type of trigger circuits. In that trigger circuits, by using UJT, how we are going to generate the triggering pulses, we will see it now. About UJT as a relaxation oscillator. We know the characteristics of UJT now. Till now we have studied the basic characters, how a UJT goes into its on state, how a UJT comes into its off state. Okay. So now we are going to make use of a relaxation oscillator. Oscillator means it is a circuit in which it generates its own pulses or its own waveform, that is known as a oscillator. Okay. Now why it is called as relaxation oscillator, we will see when we are going to discuss about this circuit. Now we are going to use this UJT. Okay. This UJT, by making use of the UJT, we are going to generate the pulses. Okay. Now let us say that VBB is the supply which we have connected. Instead of writing VE, here we are going to use a capacitor for generating the voltage. So when we are going to apply VBB across this terminal here, the capacitor starts charging through RC. Okay. And this time constant, charging time constant of capacitor, this is the charging time constant of the capacitor, tau 1, or the time constant while charging is defined by the resistance R into the capacitor. Depending on this value of R and C, you are going to find out or calculate what is the charging that can take place. Similarly, once the capacitor has accumulated the charges on its parallel plates, it is by default it has to discharge the stored energy on its plates. So for charging it has chosen this path. So for the discharging process of the capacitor, it has already been started charged here. So it will discharge through this resistor R1. It follows this path. Okay. So the discharging time of the capacitor is tau 2, which depends on R1, resistor R1 into the capacitor value. So this is how you are going to find out what interval of time it is going to charge and for what interval of time it is going to discharge. So this is the process of charging and discharging of the capacitor. Now we saw in the biasing circuit, we were connecting a terminal known as VEE, a supply voltage. Through this supply voltage we were applying it to the UJT. Now here, instead of using an external supply VEE, we are going to make use of this element C, R and C, and this part is the oscillatory circuit. Now this C is going to produce its own waveform and hence it is known as the oscillatory circuit. Now We are interested in turning on the UJT and getting out the pulses. Okay. Now at what point UJT is going to turn on? When this emitter, this voltage across the capacitor at this point, when the voltage across the capacitor will be equal to its peak value. To its peak value means how we have defined this peak value, that is for a UJT. When is the peak value? So, Vc is equal to, Vp is nothing but eta Vbb plus Vd. When this capacitor voltage will be equal to the emitter voltage, okay, emitter voltage, when it is equal, when Ve is equal to Vp, only then it will turn on. If the value of the capacitor voltage is less than Ve, it is not sufficient. The voltage developed by the capacitor is not sufficient to turn it on. So, this part, while charging of the capacitor, if you observe here, the capacitor is being charged. So, here it is not going to release any voltage across the capacitor, and hence it is not going to reach its peak value. And we know that if the voltage that is generated, the emitter voltage is not reaching this peak value, the UJT will not go to its on state. So, during this part of the charging of the capacitor, the UJT is in its off state. Okay. Now, coming back to the discharging part. Now, what happens? Capacitor is discharging now. So, it is discharging in such a way that once it reaches its peak point, automatically the diode across the emitter starts conducting, and hence what happens? The diode across the emitter allows the current to flow through it, and then the capacitor goes to the discharging part. Now, when the capacitor is discharging, what happens? Here the UJT is turned on. Once the UJT is turned on, it provides a path for the flow of current. Now we are able to get the output voltage. So, what will be the output voltage now? During the charging of capacitor, when the capacitor is working means on its parallel plates there are going to be accumulation of charges. So, during this time we are not going to turn on the UJT. When the capacitor is relaxing, discharging, already capacitor has stored its charges on its parallel plate. Now the capacitor is releasing the stored charges, and this process is nothing but relaxation of the capacitor. When the capacitor is discharging or when it is in the relaxation mode, then we are going to generate the pulses. Okay, that is, then we are going to get the output across the B1 terminal. So, this is the pulse that we have generated. Now, when this is connected to the gate of the thyristor or gate of the triac, these pulses are available to trigger the gate of the thyristor or gate of the triac. I hope you have understood how this UJT is working as a relaxation oscillator. Now, when this process keeps on repeating, okay, then what happens? There will be a pulse generated. Now, how to vary the pulses? Because we have seen in R and RC triggering method, we can vary the value of alpha. So, now how you can vary the value of alpha? Depending on the values R and C. Charging time and discharging time, we know the equations for charging and discharging time. So, if you vary RC, charging time varies. If you vary R1C, discharging time varies. By varying this charging and discharging, if you vary the charging time here, the pulses get closer and the pulses is widened. So, this is how you are going to generate the pulses using a UJT relaxation oscillator. To calculate the frequency, we have to first find out the time period, as we know that frequency is nothing but 1 by the total time period. So, the equation is given as RC is the variable, that is a components which we use for charging time, and RC log base to E VBB minus VP is the formula which we use. We already know that Vp is nothing but eta VBB plus Vd. So, when we substitute here RC log to base E VBB divided by VBB minus, instead of VP we are going to add eta VBB, take the minus sign inside. So this is the equation how it goes. Now we know that this diode is a fixed value, almost very small value, 0.6 or 0.7. So what happens to the diode value? We can neglect the value of the diode. So RC log E VBB divided by VBB, if you take it outside, 1 minus eta is common here. So VBB and VBB will get cancelled. So the time period can be calculated as RC log 1 by 1 minus eta. Eta is the intrinsic standoff ratio. By this equation or expression, you can calculate what is the frequency of the oscillator from which you are going to generate the pulses to supply to the thyristor. So this is the different circuit methods or triggering circuit methods for supplying the gate pulses to the thyristor. So this completes the turn on methods as well as the gate triggering circuits of thyristors. Thank you.